So our objective today is to understand and solve wind and water current problems. Using systems of equations. So here's my question. What has to be true in order for you to use a system, let's make it system of equations, to use a system of equations? What must be true in your problem that you would have to use a system to solve it, that you couldn't solve it just with one equation? Why would you have to have two equations? Okay, Justin Pratt? Yeah, the number of variables dictates the number of equations we have to write. So if we have two, then we're going to have two equations that form our system. If we have three unknowns, we're going to have three equations that form our system. If we have four unknowns, we're going to create four equations to help solve our system. Okay? So anytime we have more than one equation, it's called a system when we put two of them together with the same variables. So today we're going to talk about water and water current and wind problems. And so what I want to do is kind of think back to something hopefully that you've done before. How many of you have ever ridden your bike at the boardwalk on the beach? Okay. Okay, good. So at least half of you have done that. Have you noticed that there's one of two things, that going both directions, it's the same? Or have you noticed that going one direction is easier than the other direction? Okay. Okay, so why would it be different one way compared to the other? Arma. Okay. So what we have is bike riding on the boardwalk. And you found that there was an easy way and there was a hard way, right? Or easy direction and hard direction. And you guys said what caused it to be easier, it to be hard, was the wind. So let's break it down and try to figure out. Now, you're riding, so you're the one who's pedaling, right? So you have a speed, right? What is the wind doing to your speed to make that particular stretch easy? Okay, Jason?
Blowing, like pushing you.
Okay, so this would be with wind. And he's absolutely right. It's like you're being pushed. The wind is aiding you in that direction. So your speed is being added to the wind speed. Okay, and then the hard direction, you've got, again, your speed, but what's happening with the wind this time? Okay, so you're going against the wind. I also find down at the boardwalk that's the hard part. That's when the sand's getting all kicked up in your face. We used to do the heart-a-thon down there, and the kids would run down the board. Oh, you'd be pelted. You'd come home and you'd have sand all in your parts, and oh, it was terrible. In your ear, the side that was facing where the wind was blowing. Oh, it was bad. So what's happening is that the wind is actually taking away from your speed. Okay? So I want to pair a couple words that you might hear in addition to with the wind or against the wind. When you're going with the wind, I think Jason said somebody said you're being pushed, okay? So the wind is actually touching, if you're on your bike, think about it this way. What part of the body is the wind touching first when you're on your bike? Your back. And we're going to use it actually is going to get your butt first, if you think about it, because, of course, now that I say it, you can say it. Now, we don't call it the butt wind because that doesn't make sense. They call that a tailwind. Okay, so a tailwind is pushing from the back. It's going to hit your tail first, which is your butt, okay, basically, and that's where the pushing starts. Okay, and then against the wind, what's that one called?
Face wind.
Face wind.
It's not a face wind, it's a
Headwind.
headwind, okay? A tummy wind? I don't think so. Nice try, buddy. Because if you think about it, you're leaning like this, the first thing the wind's going to hit on your person is going to be your head, okay? All right, and so that's what wind does. There was a question about what happens if the wind's blowing harder than you're traveling? Well, what's going to happen?
You're gonna go backwards.
You're going to actually get blown backwards. What if your speed is the same as the wind? You're going to stay in the exact same position. Have you ever watched the birds at lunchtime? And sometimes you see them do this, and they're not moving, right? And they're just kind of slowly going. And then they'll turn and go zoop the other way. And what happens is their motion is exactly the same as the wind current. That's why they can stay exactly in the same position. When they turn, now they've got that tailwind, and it just catapults them forward. Okay? Armand?
Did the feathers help them go faster?
Do the feathers help them go faster?
They don't want to fly.
It helps them not fall to the ground and crash.
No, I mean like when the wind like goes through it, like through them, does it make them go like?
I think it's really just the force of the wind at that point.
Oh, yes.
Okay? So let's talk about water now. How many of you have ever rowed a boat before? Or a canoe, something like that, okay? How many of you have ever paddled out on a surfboard and then paddled back in?
I don't like.
Okay. So my question is, when you're rowing a boat or if you're on a surfboard, is the amount of energy you're exerting the same both directions that you go? And the answer is no. And we have the same issue because we have now water current that's going to have the same effect that wind does. And by the way, where does water current come from?
The moon.
Wind.
That's
Tide.
what tides are on.
You're thinking about tide, buddy.
Oh.
Yeah, there we go. Okay. He said the moon. Okay. So this one would be rowing a boat. Oh, that's not what I wanted to write. I'll try that again. Or paddling a surfboard. What you're going to have is an easy direction and a hard direction. And the same thing that happened with riding our bike on the boardwalk is happening with us. But instead of the wind being what holds us back or helps us, it's going to be the water current. So again, you're going to start with your speed. And when it's easy, it's because you're going with the current. So I'm going to write that over here, with current. So that would be the current speed. Okay. And if you're going the hard direction, your speed is being slowed down by the current speed. Now this would be called against the current. So you're going to hear the same sort of words as you would with wind. Now, there are other words that we use to describe with and against the current. So I'll give you one of them and you'll probably be able to figure out the other one. If you're going with the current, it's often described as going downstream. So the hard direction would be going upstream. And perhaps you've heard the expression, it's as hard as a salmon swimming upstream, okay, going upriver, because they have to fight the current. That's just how their body is wired. Well, they will go upstream to spawn, and then go, whoo, get kicked back, okay? Now, we have one more thing to talk about that is vitally important, is we're actually going to use a formula when we're talking about these problems. So can you think of a formula that you've talked about in math class, maybe even in your 5th grade class, or 6th grade class, that deals with speed and deals with traveling. Okay, Lexi, you remember? It's not distance over time how the formula normally is written. And remember, formulas do have to have an equals, but she's on the right track with the idea of distance. Amy.
Distance equals rate times time.
So all of these problems deal with, anytime we're dealing with motion, this formula shows up. I think Mr. Canody calls this the dirty formula. Or dirt formula. I've heard all different things, but it's really called the motion formula. So what we're going to do is I still am going to demonstrate how to use a chart, but this time the chart is going to use the formula, and from the chart I will actually get the equations I need to solve, okay? But the key is to remember this piece over here, okay? So here we go. A man spent, or who spent, 1 hour, oops, go back, going 8 kilometers downstream in a motorboat needed 2 hours for the return trip. So does that make sense that he would take longer to go upstream?
Yes.
Yes, because he's having to work harder. Upstream. Find the rate of the boat in Stillwater and the rate of the current. Now, honestly, there is no such thing as still water. There's glassy conditions where it feels still, but there's still going to be a wind going. Still water would only exist in a vacuum. Okay, so this is not something that is going to be an actual number you would ever experience, but this, for our purposes, how we do our math is we look for perfect conditions. Okay? All right, so we've got a man who spent 1 hour going 8 kilometers downstream in a motorboat, needed 2 hours for the return trip upstream, and then we wanted to find the rate of the boat in Stillwater and the rate of the current. So here's what I do for my chart. My two unknowns deal with rates, but they deal with a combination of rates. So what I'm going to distinguish is downstream and upstream. And then I'm going to put in my formula, but instead of writing it D equals RT, I'm going to write it RTD. Remembering that rate times time will equal distance, and that's what I'm going to grab out to create my equations, okay? So downstream, what's the rate? I don't know, and there's two things that I don't know the rate of. I don't know the rate of the boat, and I don't know the rate of the current. So what I'm going to use is two different variables. Those variables are going to be B for boat, C for current. Now that's going to be true for both of these. Now with downstream, is it a plus? Is the current helping? Or is it a minus? Is the current taking away from the speed?
Plus.
It's a plus. Okay. How long did it say that he was going to be going downstream?
1 hour.
Okay, so we got 1 hour. And how far did they travel? 8. Okay. Going upstream, what is going on between the two speeds?
Minus.
It's going to be a subtraction. How long? 2 hours. How far? 8. So what I'm going to do is this becomes equation 1. The amount of time times the rate equals the distance. And we get from here. And the reason why I'm putting time in front is because of the fact that I have a coefficient and then a quantity. So the amount of time times the rate equals the distance. Okay, you done?
Yeah.
Okay. So now this is my system. I've got two variables. Okay, so let's look at them a little bit. And so what could I do to solve this system? I got to do some stuff. Jason?
Distribute the 1 to the B and the C and the 2 to the B and the C.
Yeah, I need to get rid of the parentheses. So I'm going to go ahead and distribute. So the top guy becomes B plus C equals 8, and the bottom guy becomes, 2B minus 2C equals 8. Do I have a match? No, I'm going to have to do something to create a match. So what am I going to do to create my match?
Multiply the top by 2.
I'm going to multiply the top by 2. Now, here's what's so cool. I already have a variable that has opposite signs, so I don't need to multiply by a negative. So I'm going to continue over here, and I get 2b plus 2c equals 16, multiplying everything by 2. And then I have the 2b minus 2c equals 8. So again, I chose b to represent the boat's rate, and I chose c to represent the current's rate. And those would be pure times when nothing else was influencing them. So I've got my system, and now I'm ready to add and eliminate. So I get 4b, my c's eliminate, equals 24, and I divide both sides by 4. And I get b equals 6. So the boat's rate is 6. Now what's the label for rate? Kilometers per hour. Okay, and so now I'm going to take this and plug that number back into either original equation. I'm going to go with this guy and figure out what the current would be. So that would give me 6 plus c equals 8. Subtract 6 from both sides, and I get c equals 2. So I continue my answer, and the current is 2 kilometers per hour. Okay? And that's it. Now we could see if it makes sense. All right, what's 6 plus 2? Times 1. Does that equal 8? So it met the condition of the first equation. Okay, what's 6 take away 2? 4. If I multiply that by 2, do I get 8 equals 8? So I just met the second condition. So that just is verification that I've done it right. Now, let me give you those same two equations. Everybody ready? Okay. Let's take those same two equations. And can somebody see a smarter way of doing this problem than what we just did? What we did was fine. Anish? Okay, so in other words, we can't just move it, we have to do math. So we could divide both sides by that. Okay, and?
So it'll be B plus C equals 7.
That would be 8 because it's a division problem. Okay.
And then you can
Can we try that on the second one as well? Divide by the coefficient. Ooh. Okay, now, the reason why I bring that up, this happens a lot, where the coefficients both go evenly into the distance number. And so if you use division to simplify your equations, you'll end up having a match already. Because by nature, we have a plus c and a minus c on almost every equation that we do. Okay? Because we're talking about upstream and downstream. I have seen some rare occasions when the problem is upstream, upstream, or downstream, downstream. Okay? And they'll give you some different parameters to solve that one. Jason?
Wait, but then you get B equals 12.
2B.
You get 2b
Oh.
equals 12. Okay? All right? So that's what the problems are going to be. So here's what the one big thing that you're going to have to deal with. How do you define your variables? Now, what I've traditionally done is said B is going to be the boat's rate. And when I say boat's rate, I'm talking about boat's rate in still water, so there's nothing affecting it. And then I said C was the current's rate. And if you want to stick with mine, B and C, that's awesome. You could use X's and Y's. You could use A's and Z's. I don't care. When it came to planes, though, or things in the wind, which could be birds or Superman, I think it was in one problem we've done in the past, B and C didn't quite make sense. Because we're talking about an object up in the sky, and we're talking about wind. And so none of those letters kind of made sense. So what we have done in the past is said P is the plane's rate, and W would be the wind's rate. So when I say boat, I'm generically meaning anything that's in water. It could be a fish. Okay? And when I say P, that's anything in the air, generically. So that could be all sorts of different things that could be in the air. All right? You don't have to use these letters if you don't want. You can use your own. Armand.
So the equation D equals R times C works for wind and water?
Yes, because what's happening is things are moving. Anytime you're talking about motion, that's the formula we use. Okay? And we'll be using that formula in different types of problems when we get due back to chapter 5. Okay? All right, that's it.